Closely related to integrals that give us the arc length of a curve are integrals that give us the surface area of an object, as long as that object comes from rotating something around an axis. For instance, if we look at this bottle, we can think of this as a curve rotated around the x-axis, which is going right through here. And we can use integrals to find the surface area of the bottle. And the way we're going to do this is basically the same way we do everything in calculus. We cut up the problem into pieces that we can manage, and then we say as the number of pieces goes to infinity, we get an integral. So the idea for our surface area of revolution, that is, we've got this function f of x from a to b, and we're going to rotate this around the x-axis. Rotate it there and see how much surface area we get. And that is that we'll cut this into strips. Maybe we could call them ribbons. And each thin ribbon is basically the side of a cylinder. We've got this thin slip going around. And the area of this ribbon, let's say it's got length k up here, and let's say this is a radius r, about the line that we're rotating it about. So the area of this ribbon is, so 2 pi r will give us a circle, 2 pi r, and then k is going to give us this length here. Now this is going to be part of a curve, so we'll use arc length for k. So our integral looks like an integral from a to b, 2 pi. Now r is going to be f of x if we're rotating around the x-axis. And maybe I should put absolute value of f of x because maybe f of x is negative. And then we've got the arc length part, 1 plus f prime of x squared dx. That's if we rotate about the x-axis, or 2 pi integral of absolute value of x, 1 plus f prime of x dx, if we rotate about the y-axis. Because then so we've got this function here, f of x. If we're rotating about the x-axis, f of x is r. If we're rotating about the y-axis, x equals r. And the amazing thing is that whether we're rotating vertically or horizontally, we can always do the integral dx. We don't have to make it a dy integral if we're doing it one way or the other. And of course we could rotate around a horizontal line that's not the x-axis or a vertical line that's not the y-axis. So more generally, if we rotate about y equals c, then the integral becomes 2 pi, the integral from a to b. Now our radius is the difference between f of x and c. Well, the absolute value of the difference, because we want this to be positive. If f of x is bigger, it'll be f of x minus c. If c is bigger, it'll be c minus f of x. So that times the arc length part. And then if we rotate around the vertical line, say x equals c, then the integral is 2 pi integral from a to b, difference between x and c, and then the arc length part, 1 plus derivative squared dx. Now, let me write down what I said. So, nice fact. We can always integrate dx, whether we're revolving around a vertical line or a horizontal line. And then got this small problem. Since the human race is not that good at integrating, sometimes we end up with an integral we can't do. But it seems to me that this happens especially if we've got a horizontal line or a vertical line that's different from an axis. So especially if c is not 0. So for example, let's look at y equals square root of x. Let's rotate y equals square root of x about the x-axis. And let's do this for x between 0 and 4. So y equals square root of x goes through 0, 0, 1, 1, and 4, 2. We've got a sideways parabola, part of a sideways parabola there. So our formula is going to be, we'll have c equals 0 because we're rotating about the x-axis, y equals 0. So let's say the segment at distance x from the y-axis so some little segment here creates a ribbon with area, I guess I'd better compute the derivative and the squared derivative. So f of x is x to the 1/2. F prime of x is 1/2 x to the negative 1/2. So 1 over 2 squared of x. And f primed squared is 1 over 4x. Alright, so the segment at distance x from the y-axis creates a ribbon with area 2 pi r arc length equals 2 pi r is going to be distance to the curve, so it's f of x, which is square root of x, times the arc length, 1 plus square derivative, 1 over 4x, I guess delta x before we take the integral. So the entire surface area is 2 pi integral from 0 to 4 square root of x 1 plus 1 over 4x dx, which is 2 pi integral from 0 to 4. Let's see what we can simplify here. So that square root of x and square root of 1 plus 4x can just get multiplied inside of one square root. And so I guess we have square root of x plus 1/4 dx. So that is, let's see, x plus 1/4 to the 1/2 integrates to x plus 1/4 to the 3/2 divided by 3/2. So we've got 4 pi x plus 1/4 to the 3/2 over 3. All of this evaluated from 0 to 4. So 4 pi over 3. If we put a 4 in there, that's 4 plus 1/4, which I guess is 17/4. To the 3/2 minus, if we put a 0 in there, then this is just 1/4 to the 3/2. And let's see. So 4 to the 3/2 is square root of 4 cubed. 2 cubed, that's 8. So I can pull an 8 out and cancel with the 4. So maybe I'll do that. So 4 over 8 is 1/2. So we've got pi over 6 on the outside, and then I guess I can get rid of the fractions on the inside. 17 to the 3/2 minus 1 to the 3/2, which is just 1. So pi over 6, 17 to 3/2 minus 1. Alright, now this parabolic arc here going around the x-axis is just like the parabola y equals x squared going around the y-axis. So let's do this problem again from that point of view. The integral is going to be totally different, but we're going to get the same answer. So now let's rotate y equals x squared about the y-axis. And let's let x go from 0 to 2 so that we get exactly the same arc. So this goes through 2, 4, 1, 1, 0, 0. So this same arc, well, this different arc, but going around the y-axis. So we'll get the same surface that we got before. F of x is x squared, f prime of x is 2x, f prime of x squared is 4x squared. Now the segment at distance x from the y-axis creates a ribbon with area let's see, 2 pi r arc length equals 2 pi. R is just going to be distance from the y-axis to the curve. So if it's distance x from the y-axis, then r is x. And then the arc length is 1 plus derivative squared, which we said is 1 plus 4x squared. Delta x. Then the total surface area is the integral of this as x goes from 0 to 2. Two pi integral from 0 to 2 x square root of 1 plus 4x squared dx. Now x is conveniently almost the derivative of what's on the inside of the square root. The real derivative would be 8x. So let me multiply by 8 on the inside and divide by 8 on the outside. So if we divide by 8 on the outside, I guess we have pi over 4 integral from 0 to 2 1 plus 4x squared in the square root, and now 8x dx. So this is 1 plus 4x squared to the 1/2 times derivative of 1 plus 4x squared. So we integrate that and we get 1 plus 4x to the 3/2 divided by 3/2. Pi over 4, 1 plus 4x squared to the 3/2 divided by 3/2. And we evaluate this from 0 to 2. And I guess the fraction out here becomes pi over 6. 2 over 4 cancels to 1/2. Pi over 6. And I hope it's going to be pi over 6, 17 to 3/2 minus 1. We'll see. So we've got pi over 6. Then we plug in 2, and we've got 1 plus 4 times 4, 16. 17 to the 3/2. We plug in 0. This is 0. We've got 1 to the 3/2. So 17 to 3/2 minus 1. So yes, indeed, we did get the same answer again. Alright, so now let's look at rotating, say the same arc, y equals x squared between 0 and 2 around a different line other than the y-axis. So let's say we rotate it around x equals 3. Alright, so now the radius, rather than being x, is 3 minus x. So let's just set up this integral, the same thing with just a 3 minus x in place of the x. So 2 pi, the integral from 0 to 2, 3 minus x, because 3 is bigger than x. That's the absolute value of x minus 3, times the arc length part, 1 plus 4x squared dx. So this integral is a little bit complicated, but doable if we use trig substitution and some other tricks. Because the trig sub gives us a secant cubed. And what if we, let's just leave that as it is and not evaluate it. And let's look at what would happen if we rotated around the vertical line x equals negative 1. Or better yet, let's do the horizontal line y equals negative 1, so that we're doing a horizontal line too. So we'll take the same arc and rotate around the horizontal line y equals negative 1. So if we rotating about the line y equals negative 1, we get basically the same integral, except the radius is now x squared minus negative 1. So the difference between x squared would be the radius if we just went to the x-axis, but x squared plus 1 is the radius if we go one further. X squared minus negative 1 times the arc length part. So 2 pi, the integral from 0 to 2, x squared plus 1, integral of 1 plus 4x squared dx. This integral is also theoretically doable using trig substitution and integration by parts and some tricks. It involves secant cubed and secant to the 5th, which aren't that easy to do. So I will just leave these in the form of integrals, and if you like, you can try approximating them with Simpson's rule or trapezoid rule or whatever your favorite approximation is. The end.